Sorry.
Wait. Okay, yeah. So I'll start off with this simple problem, and then we'll go from there. Okay, so I have n1 point and n2 closed rectangles, both in the plane. And I have the property that no k rectangles have k points in common. And the question is, what's the maximum number of incidences? So an incidence is a point rectangle pair where the point lies inside my rectangle. So, okay, so that's a question we want to try to answer. And here's a very simple example. I have some rectangles, I have some points, and I mean, if you start counting, well, I did that for you already. Or this point is in one rectangle, so it contributes one incidence, that contributes one incidence. This one contributes 3. So I think if you add everything up, and I think I did that right, I should get 9 incidences, right? And I think in my configuration, no two rectangles have 2 points in common. And yeah, now the question is how many incidences, what's the maximum number of incidences that you can have? And turns out you do need some kind of condition like this. Otherwise, we can just take a trivial configuration that looks like this. And the number of incidences is just n1 times n2. Right. So this is the problem that we kind of started off with. And like I said, we do get some bounds, so almost optimal bounds, but almost. Okay. Right. So why think about something like this? And the motivation is this question in extremal graph theory, which is called Zarankiewicz's problem. And what does this question say? It says, well, if I have okay, so I denote by KKK the complete bipartite graph with k vertices in each point. So I have k vertices here, and everything is connected to everything else, right? I denote by KKK. And for fixed k, say if I have any given bipartite graph, what's the maximum number of edges that this graph can have? So G is on n vertices. For n vertices, if I have a bipartite graph with n vertices, and it doesn't include this KKK configuration, how many edges can it have? And this turns out to be related to the problem that I talked about. So this is a central question in extremal graph theory. And what do we know about it? So here's one thing that we do know. It's called the Kobayashi-Tiran theorem. Says if I have G on V1, V2, and I have the size of V1 plus the size of V2 is n, so the total number of vertices is n, and it's KKK free, then the number of edges is at most n to the 2 minus 1 over k, and some constant that depends on k. So I guess for me, the more interesting part is the exponent. And the exponent depends on k here, but it's definitely, it's better than 2, which is the trivial bound. Right. So yeah, we think that this theorem should be best possible for all values of k. That's a conjecture that it should be optimal for all values of k. And actually resolving this conjecture is one of the most important problems in combinatorics, I think. But we know, for example, that it's best possible when k equals to 2. That's when we get n to the 3 over 2. And yeah. To do that, how do we show that it's best possible? You can take the incidence graph of points and lines in the projective plane. And that shows this is optimal. And also for k equals to 3, you can take the incidence graph of points and unit spheres in, again, in finite field, and you get this bound. Yeah. And turns out, wow, this does give us some bound for our problem. So how does it give some bound for my problem? Again, I have n1 point and n2 axis parallel rectangles. Right. And I look at the incidence graph. The incidence graph is just the left-hand side. So yeah, okay, I have a picture here. Right. So yeah, so I have this configuration that I showed you before. The left-hand side corresponds to rectangles. The right-hand side corresponds to points. And I have an edge if the point lies inside the rectangle. And because there's no two rectangles, have no 2 points in common, well, my graph doesn't have a k22. And then the number of edges corresponds directly to the number of incidences. So now we reduce this question to the Zarankiewicz problem, and it gives us a bound. And what bound does it give me? It says I get the bound if no k rectangles have k points in common, then the number of edge incidences is at most n to the 2 minus 1 OK. Yeah, also, if there's any questions at any point, feel free to interrupt me. Okay, so that's a sum bound. It turns out it's way far from optimal. We can do a lot better. So I will explain how that happens. Okay, so and the general idea is this notion called geometric incidence problem. So a lot of problems, a lot of graphs that come from geometry tend to have better bounds associated to them. So that's the idea that we're going to try to use. So the bounds that are implied by the Kawai-Shorter theorem, you can improve them for incidence graph of geometric objects. So probably one of the most famous theorems of this type is the Semilinear theorem. So what's the setting there? It says if I have points, n1 points and n2 lines in R2, then what is the maximum number of incidences that I can have? So for example, if I look at the Kawai-Shorter theorem, that gives me a bound of n to the 3/2, because if I have a point line incidence graph, then 2 points define a line, 2 lines intersecting a point, I can't have a K22, so I already get this 3/2 bound. And then there's a theorem of Semilinear, which improves this to n to the 4/3. So you can do a little bit better than Kawai-Shorter, and it turns out that this is optimal. So we have a lot of configurations where this turns out to be the best possible. Okay. Any questions so far? Okay. Okay, so geometric incidence problems, there's been a lot of different results. There's incidence between points and curves, points and surfaces, like find incidences in different kinds of fields. So it turns out to have a lot of connections to additive combinatorics, distance problems. I think a lot of people here have worked on this kind of things. I don't know if I omit anyone's names, I apologize, but I think I have most people, at least most people in this seminar, so it should be fine. Okay, yeah, so again, lots of connections to lots of different areas. So it's nice problems to study. Okay, and so there's this, okay, so let's talk about what it means to be geometric, right? So one idea of what it means to be geometric are these things called semi-algebraic graphs. So we say a graph is semi-algebraic if I can look at the vertex sets. I don't have a picture, so let me try to draw a picture. So I have V1 and V2. If I can look at V1 as points, these guys as points in some dimension D1, these guys as points in another dimension D2, and there's an edge if and only if my point satisfies some system of polynomial inequalities. So that's a semi-algebraic graph. So I do have an example. For example, the point line incidence graph is semi-algebraic. Why? Because, well, if I have a point, yeah, so if I have a line B1x plus B2y equals to 1, well, almost all lines you can write like that. I can parameterize that as a point B1, B2. And then the edge relation, I can say there's an edge between two vertices if the dot product is 1.
Can I ask a question?
Yes.
So it seems to me that this is, I mean, after all, every graph is semi-algebraic by your definition, right? So it's only meaningful to define a family of graphs because you want your phi to be fixed. I mean, if you give me a graph, then I can find D1 and D2 and polynomial inequalities that should satisfy it.
Right. Yeah, I guess in the theorem, we say that things are bounded by some constant. Is that all right?
Yeah, the complexity of the description of it has to be bounded.
Yeah, the complexity has to be bounded, yes. So I think I will say that when I guess I should say that here as well. Maybe I can say that here. Well, the system of polynomial inequalities, the number of inequalities is bounded.
So and also the dimension. I mean, you could call it probably D semi-algebraic, and everything is bounded by D. The dimensions, the degree of the polynomials, everything is bounded, right? And then it's
right. So some complexity where the degree is bounded and the degree is bounded. Is that, I think that's everything we need to cater for, right? The number of inequalities is bounded and degree is bounded. Does that make sense?
Yeah.
Okay. Right. So again, yeah. So point line incidence graph, that's semi-algebraic. And then, right, there's this big theorem of Fox, Bach, Scheffer, Suk, and Zell. It says, well, if you have a semi-algebraic graph, okay, well, I did need to say that. Everything, the degree and the number of inequalities is bounded because I don't say it here, right? So if I have a semi-algebraic graph and it's KKK free, then the number of edges is bounded by 2 minus some constant. And this constant only depends on D1 and D2, right? So remember what the Kobayashi-Turan's theorem said. It said the exponent is 2 minus 1 over K, but now the complexity only depends on, the exponent only depends on the dimension D1 and D2, and the K shows up in my constant. Yeah, so, and this turns out to be a common generalization of many incidence results. So again, this implies some bound on what I can say about my rectangles problem. So remember the Kobayashi-Turan said, I can get 2 minus 1 over K. And now, again, I can write the point rectangle incidence graph. It's semi-algebraic. So I can identify axis pair rectangles as points in R4. So I get the semi-algebraic graph in R2 times R4. And it turns out if you plug the numbers into this bound that into this theorem that I just mentioned, then you get a bound that looks like n to the 10 over 7 plus epsilon. So this is just plugging the bound into what the bound, these numbers 2 and 4 into what the bound was previously. So you can already do a lot better, right? We had, the last thing we had was n to the 2 minus 1 over K, exponent dependent on K, but now we've basically have a fixed exponent for RK. Okay. Right, but now we can say, well, we should expect, why should we expect to do better? So here's one reason why intuitively it should be possible, because if you look at the point line incidence graph, well, it's defined using the inner product. So we're using addition and multiplication. But in my point rectangle incidence graph, the only thing I'm using is ordering, right? Not much else. So if you think about it, it's somehow a much simpler relation. So hopefully we can say something about this. And that is what we do, in fact. So our result says the following. Okay, if I have n1 points and 2 closed rectangles in R2, and again, there's no KK, K, and then how many Ks did I say? I don't know, KKK, 3 Ks in the incidence graph, then the number of incidences is at most linear, almost linear. So n log to the 4n. So again, that's a much, much better improvement. Like it's basically almost the best possible you can say. You can definitely do linear.
Okay. Can I ask something?
Yes.
The previous bound you said works for arbitrary rectangles, not necessarily axis parallel rectangles, right?
No. Does it work for arbitrary rectangles? No, it does not. I mean, you can get, if you just plug in these numbers directly, I guess, you can get a better bound of n to the 4 over 3 for arbitrary, like using.
But it's a semi-algebraic.
Differently, I guess you can get n to the 4 over 3.
Isn't it a semi-algebraic graph as well? I mean, you just maybe.
Yeah, arbitrary rectangles is semi-algebraic. Yeah, but you cannot do linear for arbitrary rectangles. Yes.
No. The previous bound, the n to the 10 over 7 or whatever.
Yeah, you can get that for. How do you parameter for now? I guess how would you want to parameterize arbitrary rectangles?
So the dimension changes. It's no longer.
Yeah. So you get a different.
You get something better than the Kobayashi-Turan. That's what I wanted to say.
Oh, yes. Yeah, you can definitely get better. Yes. Okay. I'm not sure what you can get.
It works for any polygons. Yeah.
Yeah. Okay.
Right. So good. For rectangles, here's what we can say. Axis pair rectangles. Again, like Shahar said, you can get at least the Fox, Park, so Scheffer, Zhao bound. It gives you some bound for arbitrary rectangles. I don't know what the exponent should be, but yeah, you can figure it out.
Can I ask a question?
Yes.
These bounds, can they depend on the, so this semi-algebraic relation, right? It defines a semi-algebraic set. So do these bound can they be made to depend on the dimension of the set? So for example, in the ordinary Zemerelli-Trotter theorem, the dimension of the incidence variety, I guess, is 3. And somehow this 3, and so but I guess for rectangles, you have only inequalities. There are no equations. Is that correct?
Yeah,
so that's
so
important.
You have, well, once you took arbitrary rectangles, then you have equations. Are we just talking about axis per rectangles? Then you have only inequalities, right? But I'm not sure if, I'm not sure I understand the question. What do you mean? Can I make it depend only on the set?
No, I mean the exponent, should it depend on the dimension of the semi-algebraic set that defines, I mean, the
I see, okay.
The relation. Okay, I mean, we can take this offline.
I suspect yes. I think you can make it depend on the dimension of the semi-algebraic set, but I won't bet my life on it.
But can I ask a question? So the R4 is because you have two vertices determining the rectangle in
yes, that is correct.
But it would be R6 otherwise, right?
Yes, otherwise it will be, is that right? Should it be R6?
Maybe so you have 3.
You can do 5 because you can take an axis parallel rectangle and then rotate it, which edged only one.
Oh, I see. Yeah.
Okay, there you go. Oh, yeah. So I don't know.
How would that change the exponent of the solution?
Oh, it would be worse. I don't remember the numbers off the top of my head. Do you remember, Adam?
It's not easy to calculate.
Okay. Yeah.
No, it's slightly worse. Yeah.
Slightly worse.
Kind of expression if you want.
Yeah, I mean, you can plug it in, or like maybe offline we can do that. Okay. So, right. Okay. Good. Any other questions? Right. I
guess that's just a follow-up question. I mean, how much of this is really dependent on these things being rectangles or
nothing
arbitrary? So it really should be the dimension of the set semi-algebraic relation. Is it?
Wait, sorry, say that again.
So you have some kind of incidence relation, right? This incident, it's coming from the geometry of the rectangles, but so is it really anything to do with the rectangles, or it's just some arbitrary semi-algebraic relation of the same dimension, but maybe you have to throw away some lower dimensional parts, which you do in this case for the cuboid. And then the same exponent would apply. Is that correct? Or there's some geometry of the rectangles that's involved in this?
If you prefer, I can answer, up to you.
Yeah, you can answer. It's your thought.
So yes, it's any constant, like as long as the complexity of the semi-algebraic relation is bounded, it's fine. But it's not just one dimension. We have here 2 dimensions, and it's not like 2 and 4 would give you the same bound as 3 and 3. It's not both dimension matter.
But the rectangles is not so important.
No. Not at all.
Right.
Rata is already taking it to the minimality setting.
Right, the rectangles sort of become important on our result, I think, or the ordering becomes more important. Okay, right, so good to move on. Okay, seems like it. Good. Right, so what do we prove? We show this n log to the 4 n bound. I think I'll mention this later, but yeah, so this is for any point, any set of n1 points, any set of n2 closed rectangles with axis parallel sides, no k in the incidence graph. That's what we get. We have a slightly better bound. So if your rectangles are what we call dyadic, so this is a more combinatorial argument. If your rectangles are what we call dyadic, they're products of intervals of the form like dyadic intervals. Not very important what that is. Then we can get a logarithmic bound. So n log n divided by log n. And this one we actually show is close to optimal. So we have a construction of dyadic rectangles that gives the same bound up to some constant. So this guy is K22 free, and it has n log n divided by log n edges. So at least for the direct case, we have matching up and lower bounds. For arbitrary, like arbitrary axis parallel rectangles, we're not sure if this log n factor is tight, or the 4 should be there or not. So I guess that's an open question. It's like, does this lower bound hold for arbitrary rectangles or arbitrary axis parallel rectangles, I guess?
So the dyadic rectangles is not a semi-algebraic graph, right?
No.
So that's in a different setup. Okay.
Yeah. Yeah. So this argument, that's purely combinatorial, and we use different technique for this guy. Right. And the lower bound here, and I would think probably you can lower this to n log n. And actually, there was a result right after ours. Tomon and Zakharov, and they improved this bound to n log n for k equals to 2. And again, they have purely combinatorial arguments that use these notions of separation dimension and Mach dimension, poset dimension. And somehow they end up using our construction, but I don't really understand it too well. So yeah. So again, this bound, you can improve it to n log n. For the case k equals to 2, I suspect you should be able to improve it for every k, but I don't know how to do that.
So is this dyadic result just because you're removing a number of parameters needed to describe the rectangle?
No, the dyadic result just follows from, it's a completely different argument. And I think you should get the same bound in general. So I don't expect it to be special.
Because if you had, let's say your rectangles were replaced by, say, one-way open rectangles, so that one side goes to infinity. That way, in that case, you could just specify the rectangle with 3 parameters, and
right,
you get a lower bound.
Yes, in that case, we can actually get a better bound of n log cubic.
Cubic, yeah, okay, that's what I thought, something like that.
Yeah. So the next result I talk about sort of says how we get this result, and this, well, it's always going to be linear times some logarithmic power, and the power of the log depends on how many inequalities you have. So if you have open-ended ones, then you get 3. Okay, so that's the incidence result that we have. And okay, and this is a consequence of a much more general thing. So what's the much more general setting? Again, I have the exact same setting of a semi-algebraic thing, but now I say my inequalities have to be linear. So it's semi-algebraic, but linear inequalities. Or equalities. And in this case, well, so I have a semilinear, that's what we call a semilinear graph. Semi-algebraic, but everything is constrained to be linear. And what we end up showing is if I have a semi-algebraic graph, semi-linear graph, and it's KKK free, then the number of edges is n times log to the Cn, and we can specifically say what C is. C is precisely the number of linear inequalities in my defining system. So for example, the reason we have this n log to the 4n is because to specify an axis power rectangle, you need 4, right? And like I said, if you have an open-ended, like one-way infinite guy, then you could make it 3. But something we're not sure about is, does this, okay, so let me talk about this open question. Does this C need to depend on the number of inequalities? Is there a bound independent? Is C independent? Oh, okay, can the power of log be made independent from the number of inequalities? I'm not sure what the answer to that question should be. But again, you have a semilinear graph with C equations, you can get this bound. And actually the theorem we get is a little bit more general. What we do is we work over any ordered division ring instead of the real numbers. And we also consider these functions that are a lot more general, which we call coordinate-wise monotone functions. I don't think but okay, very roughly what it says is if you restrict to either coordinate, let's say if I restrict to some coordinate here and I put in, then the ordering I get for any value, if I plug in any value from RD1 into the first coordinate, the ordering I get on the second coordinate is the same. That's basically what these conditions are saying. So restricting to either coordinate should give you the same ordering on the other coordinate. If you have this kind of function, we can get better bounds, but again, not very, very, very important.
So
yes.
I'm just trying to understand the ordering.
Okay, so what I'm saying is I guess, yeah.
Oh, okay.
So for any AA1, if I plug in AA1, A and A prime in the first coordinate, then the ordering I get on the other side should be the same, right? And this should be true for both coordinates. So it's a little bit more general, but I mean, at least for my purpose, it's not. Okay. Yeah, but the big question I think you should probably, if you want to think about this, is like, can we improve the power of log here? So I think I will mention that. Okay, yeah. So maybe I can quickly talk about a very restricted case of theorem 2. So this was theorem 2, the big bound that we have, or the main bound that we have on semilinear graphs. And the idea is not too hard. Getting it to work is a little bit tricky for general things, but maybe I'll quickly talk about the idea. Okay, so let Fsn be the maximum number of edges in the KKK free graph on n vertices, and I have S linear equations. And what we do is we do an induction on S. Okay, so the base case is fairly simple. If there's no linear equations, then I have a complete graph. So like at most k times n, that's not too hard. Right, what do we do then? We say, well, we show this inequality. So Fsn is at most twice of Ssn over 2. And so in one case, we're going down in the number of vertices, and in the other case, we're going down in the number of inequalities. Right? And essentially what we end up doing is use the order structure of the real numbers to split up the graph in some nice way and control the incidences in each of these parts. So maybe a little bit more specifically, what do we do? Suppose I have L, which is one of the defining inequalities, and I can assume that L is of the form L1x is less than L2y. Right? This is because things are linear. And then, well, I have L1 maps V1 to the reals, O2 maps V2 to the reals. So like, I have a picture that kind of looks like this. So I have this set V1, I have this set V2. And what I do is I cut up my set into 2 equal pieces. So I have half my points on the left and half my points on the right. Right? And then remember, L looks like L1x is less than L2y. So what can I say? I can look at different pieces and say what's happening. So for example, let's look at this guy, V1 plus and V2 minus. This is never going to be satisfied by my inequality. So there's no edges going between these two parts. Like this part is going to be complete because every point here is less than every point here. And then, so that gives me the second part. Now I go down in the number of inequalities. So the number of edges here depends on what happens with other inequalities. And then lastly, well, what's happening inside here or inside these two pieces, I've gone down in the number of vertices. So I get the number of inequalities stays the same, but the number of vertices go down. So again, very rough idea of what's happening, but this gives me what I want. It shows that the inequality that I said I needed to prove. And then from here, the bound that I mentioned is not too hard to get. So does that roughly make sense? Okay, yeah, so getting this to work more generally takes a little bit more work, but that's roughly the idea of what we go with. Okay, so that was all about graphs. We have a slightly more general theorem that talks about hypergraphs. So we can talk about the Zarankiewicz problem for hypergraphs. And then we say, okay, if I have an R-partite or uniform hypergraph, so I have R parts now instead of 2, and I have edges that go across. So they have one vertex from each part. And on n vertices total. And now it's k free, bunch of k's now, right? Which is the obvious thing that you would think. Then there's a theorem of Erdős, which says that the number of edges is n minus n to the r minus 1 over k to the r minus 1. But again, what we should roughly think of is, well, it's n to the r is the trivial bound, and you can improve this bound by some factor that depends on k. Right? Okay. And again, you can ask, well, if my hypergraphs are nice for the semi-algebraic, can we do something? Oh, right, okay. So even before that, this thing is basically almost essentially tight. And there's a probabilistic lower bound that says you can't improve this. You can only improve it up to a constant, not too much more. But again, if we move to semi-algebraic graphs, then there's a theorem of Tao-Dou, which says that this constant, again, I can make it depend on d1, d2, up to dr. The n to the r minus c, and where c now depends on d1, d2, dr, and it does not depend on k. So it's a significant improvement on the, and we know you cannot do this for arbitrary graph, hypergraphs. Okay, so we have that for semi-algebraic hypergraphs. What we can say for semilinear graphs is essentially, again, almost best possible up to constants, but what we can say is, if I have a semilinear hypergraph, then the number of edges is bounded above by n to the r minus 1 times some logarithmic factor, where the power of the log depends on, now it depends on the arity of my graph r and the number of defining inequalities. Right. So that's the extension to hypergraphs. And what can we say? Yeah, so maybe a little bit about the proof. Now, again, it's an induction, but now it's a double induction on the uniformity and the number of inequalities. So again, we have this divide and conquer strategy. So remember, for r equals to 2 for graphs, I reduced to a graph that has smaller v1 plus v2, right? On the left, I had in v1 plus v2 was less than a half times n. On the right, it was at most a half, at less than half times n. For r equals to 3, again, we need to do some sort of reduction. And what we end up doing is we try to reduce to a graph that has a smaller quantity that looks like this. So v1 times v2 plus v2 times v3 plus v3 times v1. So on each part, so I divide my graph into 2 pieces. On each piece, I have, like, I can bound this guy. And then again, we show an inductive inequality of this form, and basically the same thing as before. And the bound follows from this. Okay, that might be a little bit too vague, but hopefully at least gives a general idea of, like, this divide and conquer strategy is, I guess, one of the more important things that we come up with to try to bound this graph.
So do you also, again, make this conjecture that the C should not depend on the number of inequalities? Or?
Yes, well, C should now probably depend on the arity, but again, we don't really have too many examples for hypergraphs. And
but about the number of inequalities? Probably
not. Well, actually, I don't know. I cannot conjecture if it should depend on, it should not depend on. So yeah, I wouldn't be surprised either way. So for example, do I mention this anywhere? Here's a question on that. Can we find a set of axis parallel boxes in 3 dimensions? So is there a set of boxes in our points in boxes? Or is there a family of sets in R3 where the number of incidences is, I think I mentioned this somewhere, but I don't know when I mentioned it, but the number of incidences is strictly bigger than n log n. So maybe it should be this, I don't know. But we could not find anything that's better than the example we have for R2. Everything we have in R3 still gives n log n. So, and that seems like a very simple question. We tried really hard to find an example, but we couldn't do one. So it's entirely likely that there is one. But if we can find this, if we can show that there's a set of boxes in R3 that needs more edges, that would suggest that the number of this log power should depend on the number of inequalities. But yeah, I don't know. Okay, so that's what we can say for hypergraphs. Right, okay, so that's the two big theorems. And again, we have a bunch of consequences in combinatorial geometry and also maybe model theory. So I'm afraid to talk about model theory now because I forgot I was going to just, but okay.
No.
Yeah, so what can we see in combinatorial geometry? So remember I talked about axis pair rectangles, but what we actually have is much, much more general. So suppose I have some set of polytopes and I tell you that the faces of the polytopes come from a prescribed set of directions. So these polytopes, they cut out from half spaces that have normal vectors in some fixed set. So your polytopes, so if you have pentagon and the sides of the pentagons are all parallel to some fixed set of directions, or in high dimensions, you have polytopes, but the faces are restricted to come from some finite set. Then the incidence graph does not contain a KKK, and the incidence graph does not contain a KKK. Then again, we can bound the number of incidences by almost linear. It's n log, the n times some log factor of n. So it's a very strong result in some sense. But again, the restriction that the faces have to come from a certain set of hyperplanes with fixed slopes. Right. So we have that. Maybe, and the proof basically just reduces to this. You can write this as a semilinear hypergraph. So I won't talk too much about that. Right. So yeah, maybe I'll skip the proof. No, okay, yeah, here was the question I was just asking. It's like, if there's a set of endpoints and n boxes in R3 that have more incidences than log n. So maybe if I put it one slide. Well, we don't know. Okay, so here's another question that sort of, or here's another result that sort of follows. It's about the unit distance question. So the earliest unit distance question says, well, in the L2 norm, what's the number of unit distances? And the conjecture is it's almost linear into the 1 plus epsilon. And yeah, so maybe some history about this problem. Maybe I can skip that. Oh, okay, no, I don't think I can skip all of it. But so yeah, the unit distance conjecture, the unit distance conjecture says how many unit distances can you have among endpoints? And it says it should be almost linear. And you can ask the same question in high dimensions. So for example, in R at least 4, it's possible to get n squared by taking your points on 2 orthogonal circles. So half your points on one circle, half your points on the other one, and you get n squared unit distances. But there's this result of Fox, Park, Sheffer, Fook, and Zhao, which says, well, if any pair of orthogonal circles of some radius contains fewer than k points, so essentially, if you're kind of far away from this configuration, then the number of unit distances is small. You can't have too many of them. And what we can do is, if you replace the L2 norm with polygonal norm, so the L infinite norm, for example, then you can have the same thing. You can have, well, you can have a configuration that looks like this, and you can get n squared distances, unit distances, right? So if I put my blue points and green points, every blue green pair is at distance 1. And what we end up saying is, well, if you don't have a degenerate configuration like this, then you can get almost linear number of unit distances. So essentially, there's a theorem that says, well, for L1 and L infinite norm, you can get n squared, and well, that's the best possible. But as soon as you stop this configuration from happening, we can basically drop down to linear. So yeah, so some stuff in combinatorial geometry. I guess maybe I can talk about some connections to model theory. This might, okay. So, okay, yeah, so 2 of my co-authors are model theorists, and the reason they're interested in this is, well, maybe I'll try to explain a little bit of that. So what do model theorists do? They study structures. So you have integers under addition or complex numbers under addition or multiplication, and they consider the set of all first order sentences that are true inside that structure. And that's referred to as the theory of your structure. And what model theorists try to do as well, try to understand what structures come from certain theories. So for example, if I have 2 isomorphic structures, then they should have the same theory. But if I have the theory, which is the set of sentences that should be true in my structure, then you can have a lot of different structures. So, okay, for given an infinite structure, there's at least one structure per infinite cardinality with the same theory. So if you give me a structure, I can find a different structure of every infinite cardinality that satisfies the same theory. So for example, like maybe people are aware of these things called the real closed fields, all of which have the same theory as the real number. So the algebraic numbers, or countable, hyperreal numbers, computable numbers, and so on. All of them have the same first order theory of the real numbers. Okay, and the basic, like, or one of the more basic questions, I guess, is what can we say if for some uncountable cardinality k, there's exactly one structure that has that theory. So if I say, okay, here's the theory, there's exactly one structure of some cardinality k that satisfies this theory. And so such structures are called like tame structures. Like a lot of model theory tries to study this kind of structures. Okay, so like here's one consequence of tameness in that somehow these so I don't know, like if you look at theories and first order things, it's very abstract and vague, at least to me. But these things tend to have very combinatorial consequences. And so, like, for example, like one consequence of tameness is if you look at graphs that are definable in these structures, so graphs with edge relations or formulas that are inside these structures, then these graphs are much simpler than arbitrary graphs. So for example, for these tame structures, we can get like much better regularity lemma type statements. There's improved bounds on Erdős-Haino problems, on Zarankiewicz problems. So like some of the stuff we've seen so far from semi-algebraic graphs and so on, that fits into certain model theoretic frameworks that talk about tameness.
Okay, but wait, Abdul, one thing is that I thought you were talking about in your prior discussion, entirely finite graphs. I mean, all the theorems you talked about in model theory, they're all they're infinite structures. I mean, this notion of having a single model, it's called categoricity, but it's not true. If you have a single model in one uncountable cardinal, it's true for every uncountable cardinal, but it's not true for finite models. You may have no finite models.
Yes, but what we do is when we're looking at graphs, we look at, we restrict to a finite subset and look at the graph for that setting.
Yeah, but virtually no theorems for model theory hold for finite graphs or finite models. They're always in. So I don't know how any.
Oh, not for finite models, but you can take a relation that's definable in your infinite structure, and then you can restrict that to a finite set.
Okay. Go on. Maybe I'll.
Is that?
So I have one.
Keep going, I guess.
Okay.
But I have a basic question. So. Yes. The theory of real closed field is not categorical, right? Because in uncountable cardinalities, you can have many non-isomorphic models. So,
right.
So that means you are omitting from this discussion all the semi-algebraic stuff.
Yes. So I'm not trying to be very formal here, I guess. Yeah. I mean, I'm just trying. I guess what I'm trying to do is just give an idea of how these things. So I guess the next thing I want to talk about is what am I talking about? Like NIP structures, and then there's these like bounded VC dimension kind of things. And then there's these things that talk about, what do you call it? A Zarankiewicz problem for bounded VC dimension graphs.
Yeah, but so is it really true the categoricity is important in all this consideration? Because the NIP is not related to categoricity. Whereas the algebraically closed field, real closed fields, they are both would be NIP. Yeah. But okay, I mean, okay, go on. I mean, it's just I haven't seen categoricity in this context before, so that's what.
I see. Okay, so I might be saying wrong stuff. So if you have questions, you should definitely ask or like say something, because this is my understanding of model theory. Right. So I guess this is what I mean by definable graph. But again, you have formulas, and edge relation is given by these formulas inside my structure for the first order formulas. But I guess so one example I have is this NIP structure which is the structures where there's exactly one structure of every uncountable cardinality satisfying that theory. And then we know that every definable graph inside such structures have bounded VC dimension. And the structure has no independence properties. Every definable graph has bounded VC dimension. So these are like combinatorial characterizations of what it means to be an NIP structure, I think. So now, example of NIP structures, real closed fields, p-adic numbers, algebraic closed fields, algebraic closure of finite fields. And then, well, another theorem from this Fox, Park, Sheffer, so Zhao paper that I keep mentioning is that if I have a graph that has bounded VC dimension, then the number of edges in this, and it's KKK free, then the number of edges in this graph depends only on only on the dimension, on the VC dimension. So in some sense, I think of that as saying, okay, well, if you have a graph that's defined with an NIP structure, then you should have, it's a simple graph in some sense.
But just to make clear, the first two examples, real closed field and p-adic numbers, their theories are not categorical. I mean, they are NIP, but not categorical.
I see. Okay. So yeah, so this should not have anything to do with categoricity. And then there was this recent theorem of Janzer and Pahota, which improves this bound a little bit. So what does that say? It says if K and D are both bigger than 3, then you can actually do a little bit better. So you can have little o. So it's strictly smaller than n to the 2 minus 1 over d. So this is a recent, well, from last year now, I guess. Last year, this year, last year. It was on track. Yeah. But so I guess here's an interesting open question that I don't, it's probably hard, but what should this be? Like, what should the exponent be here? Right, if well, they just say it's little o of 2 minus 1 over d, so they don't give it, they don't quantify exactly what it should be, but I mean, I think it's an interesting problem to actually quantify that. I'm not sure if many people have thought about this problem. Okay. And then, so that was NIP structures. Then there's this notion of distal structures, right, in which formulas admit this thing called a definable cell decomposition. So again, I probably can't define what this is too precisely, but it generalizes somehow the notion of cuttings and partitioning polynomials. If you know what those are, good. Otherwise, maybe you don't need to worry too much about it.
I have a question.
Yes.
Won't the Janzer-Pahota result fall under distal instead of NIP? In NIP, I think you can already do better in other ways.
But it's bounded VC dimension, right?
So that's distal, right?
No, distal is stronger than that.
No, distal and NIP are unrelated. For example, the theory of algebraically closed field is NIP, but not distal.
Right.
While,
are they completely unrelated, or is distal a subset of NIP?
No.
Okay.
They are, but one question about this theorem C.
Right.
So this VC dimension is related to the formula underlying the definition of the graph, right?
Right.
So again, it's like instead of saying D semi-algebraic, this graph is some kind of phi definable where you have a relation phi, and the VC density or dimension of this phi is D.
Yeah.
Yeah.
So I guess I have a question for you. If I have a, I don't know, NIP theory, and I look at a graph definable in it, can I get in, I don't know, some fixed NIP theory, I guess? Can I get an absolute like bound on the VC dimension of this thing, or is it just bounded? Like it cannot be infinite?
No.
Can it be arbitrary?
So it can be arbitrarily large. I mean, right. So it's like the VC density. Yeah, so it depends on the arity. For example, it will depend on the arity of the formula.
I see. Okay. Right. So, but okay.
But here's that question. These theorems. Can you go back just a slide? These
Yes.
theorems, are they expressible in the first order language of these theories? I mean, you're talking about this theorem, say, over real closed fields. You're saying that this is a first order, it can be expressed in the first order theory of these real closed fields?
No, it's just saying that if you have a graph that is semi-algebraic for some fixed complexity semi-algebraic, then, and if that formula that defines that relation has VC dimension D, then this is the upper bound. So the theorem itself is not first order expressible. It's just that it's about definable graphs in whatever structure he is in.
I see. Okay. I see. Okay. Yeah, go on.
Okay. Right. So maybe I can ask you about this offline. But in a dist, so there's these things called distal structures, which sort of have this thing called a definable cell decomposition. And I think, at least in my understanding, these generalize the notion of cuttings in polynomial partitioning. So like real closed fields are distal, p-adic numbers.
Yeah. So except that it's a generalized notion of cuttings, but not really a polynomial partitioning, because we really do not know whether there is a polynomial partitioning type result for O minimal, for example.
Okay. And then, right, but for example, I think the key point here is algebraic closures of finite fields are NIP, but not distal, right? Which is why you can get improved bound, even better bounds in distal structures. So there's this theorem of Chernikov, Galvin, and Starchenko, and at least my understanding that generalizes this Fox-Parks-Sheffer-Zhao theorem to this setting of distal structures. So instead of they use this notion of definable cell decomposition to improve the bound even more than the bound that we have from before. But somehow what they end up doing is they use this VC dimension bound to build up. And so, maybe I can talk to you about this later. But
so this is basically NIP, not distal, this result, right? Because they are assuming that there's some more information about the sets.
Yeah, so they like NIP and distal, I would guess, but somehow that seems very weird because they use this VC dimension result as a bootstrap thing. So inside the cells, they end up using the bounded VC dimension thing. So I'm a little bit unsure about how things work then. But maybe Sugata has something or like understands a little bit more. So because in my, and from my understanding, because they were using the bounded VC dimension thing inside the cells, I was assuming that says something about distal structures and being related to NIP structures, but I could be wrong here. And then, right, so I guess that's what we know for distal structures. And then in some sense, what we have, the reason why these model theory people were interested in what we did is because it characterizes something called modular structures. So like modular structures, basically they don't encode fields, so they act more group-like. So if you have something like a group, you can't have, well, you have addition or multiplication. That's sort of what the modular structure is. And then there's some more deteriorated thing about what it should be. But part of our thing is, well, okay, so here's another theorem that we have, which follows from what we did, is if I have a weakly modular O minimal structure, and I have a graph definable in M, if it's KKK free, then it should have a linear number of edges. Yeah, and then if I can find a graph that has like strictly more than n, like n to the 1 plus epsilon edges, then you can then it encodes a field in some way. So the only way you can get more than a linear number of edges is if you have some sort of field-like structure going on inside the theory. So you need addition and multiplication to do both of that. So in some sense, it's like this sum product phenomenon going on, like having a linear number of edges for all your relations means you must act like group in some way. Yeah, that's basically like some very vague overview of model theory. So hopefully that makes some sense. And I think I will stop here.
Thank you.
Yeah.
Yeah, I just wanted to make a clarification because it didn't come up and maybe I said something. So it is true, I guess, that every distal structure is also NIP, but NIP structures need not be distal.
Yes. So
and what I had in mind about the orthogonality is another type of things that model theorists are interested in, property of theories as stability. And stability and NIP are kind of orthogonal. So you can have one without the other.
What is stability?
Okay, that makes sense. But there's also like even stability seems to imply more combinatorial things, right? There's all these stable regularity lemmas and things like that.
Yeah.
So
what is
stability? Yeah, stability roughly means that you cannot define order in the